in this seminar. Today in this seminar, we will see how artificial intelligence helps us use satellite data to get not just near real-time precipitation estimates for the whole continent of Africa, but also how we can capture inherent uncertainties in these precipitation estimates. And this ability to assess the uncertainty will help us to spot extreme events, which is something that's becoming more and more important in our changing climate. So as John said in his nice introduction, I am connecting from Gothenburg, Sweden, here really up north in the globe, which is also where Chalmers University of Technology is located, a PhD student there at the moment. As it was said in the introduction, I'm focusing on space-borne retrievals of precipitation on ice clouds using machine learning techniques. And something I also want to mention is I'm also working in an European AI project that is named Enfield, where we work with topics like trustworthy AI, green AI, human-centric AI, which I think some of you can find interesting. So I encourage you to check the website if you are keen on doing that. In any case, in this seminar, we will go through different points, which I list in this slide. So first of all, we will cover why we need something that I call RainOverAfrica. Then to get everyone more or less on the same page, I will talk a bit about satellites. And then our artificial intelligence or a statistical approach to estimate precipitation from space using satellite data. Then we'll cover how we developed RainOverAfrica, or ROA, as I will refer to it in short. And afterwards, we will see an example of how we can get a near real-time precipitation estimates with this RainOverAfrica tool. And to begin with, I want to highlight that ground-based coverage is insufficient for estimating precipitation. So in the map here, we see the distance from the nearest gauge in the Global Precipitation Climatology Center. So gauges belonging to this project, GPCC gauges. And we see that there's quite a lot of white space. Ideally, this is Germany, this really blue area. Ideally, we would like to have something like that. But this picture can even be misleading, because if we were to join all the rain gauges that are in the world belonging to different projects, but in this case, if we focus on the GPCC project, we see that their area doesn't even cover half of a football or soccer pitch. So it's a very, very small area that is covered by rain gauges. So we need to turn to remote sensing. And for that, we can use ground-based radars, which is what is shown in this picture, where the highlighted areas show more or less the ground coverage by weather radars according to a VMO database. And here we see that Africa is unfortunately not well covered by ground-based radars according to this database. So we need to go to space to have a continuous coverage of Africa for precipitation estimation. And for that, we have the Global Precipitation Measurement Mission, which I'm showing in this animation. What you are seeing here is the orbits of different satellites that belong to this GPM constellation. And these satellites have instruments that allow us to estimate precipitation from space. But there is a small challenge in this mission, which is that it takes quite a while to get a new precipitation estimate because of the orbit of the satellites. But I will just pause this video. But we have geostationary satellites. And here Africa is in a privileged position because it has a geostationary satellite, the Metasat satellite, that is constantly observing Africa. So geostationary satellite is, as it is shown in the video, a satellite that is rotating, it is orbiting with the Earth, and it is constantly looking at one side of the world in this case. And for this satellite, we are constantly able to see all of Africa. But geostationary satellites, they are not as good as satellites that belong to this constellation to estimate precipitation. So RainOverAfrica is a project or a method where we aim to estimate precipitation from space for Africa in a way that we get immediate estimations, precipitation estimation, and that we have a continuous evolution of precipitation over Africa. And we are able to do that because we use this geostationary satellite. What you see here is an animation I put together of the images that we can get with the satellite. And again, what we get with RainOverAfrica is, as the name says, rain over Africa, but also quite important is that we are also able to get uncertainties of precipitation. So obtaining precipitation from space is nothing new. For comparison, there is the GPM USTM IMERC product, which I would consider is quite an established product, but it has some constraints. So for example, to get a precipitation estimate from IMERC, their website says you have to wait at least 4 hours, and this can go up to 4 months depending on the flavor that you want to have of IMERC, because it comes in 3 different versions, if you wish, and that is because of the data sources that they use to produce their precipitation estimates. In any case, estimating precipitation from space, that is a complex problem. And one reason why it is a complex problem is because we cannot measure precipitation directly. We need to execute retrievals. And to explain this or to illustrate this, I want to use this example. So in this plot that I'm showing here, I'm showing an image that is taken by a geostationary satellite. And on the right, we have some reference precipitation data. This was obtained with also a satellite specialized to quantify rain. For the sake of the presentation, we will assume that this is an absolute ground truth. Now, mapping this to this or this to this, independent of the direction, can be complicated because we will find that we can have one value can correspond to multiple. One value from here can correspond to multiple values here and the other way around. So there is often not a unique solution to the retrieval problem, which makes this what is known as an ill-posed problem. This also causes that in the retrieval of precipitation, there is inherent, so irreducible uncertainties, which we ideally need to deal with. And for that, we can, of course, use statistical methods, but the statistics of precipitation are often non-Gaussian. So they show a distribution that is usually skewed, and also precipitation, the range of values that are of interest in precipitation covers orders of magnitude. So A unit that is often used when quantifying precipitation is the millimeter per hour. So that is the rain rate. And this can go from 0.2 millimeters per hour to 2 millimeters per hour up to 20 millimeters per hour, depending on the range of interest that you are interested in. And the statistical method that we have been using at Chalmers to quantify precipitation is the following one. And I want to use a general example to explain the method that we have been using in case you are working with some other quantity that is not precipitation, so that you can find this hopefully interesting for your application or for whatever you are working with. So let's say we want to estimate precipitation from some satellite data in a supervised fashion. And we have a training data set, and we plot this training data set. And let's say it looks like this. So if we try to find a function f that approximates the satellite data, for example, using a mean square error loss, we will get something like this, like the blue line. And while this can do a good job of telling what we expect on average to happen when we have a satellite data value of 2, remember this is a made-up value, just an example. So while this mean square error loss can get us a good value for what to expect on average here, we fail to capture this spread. So this uncertainty in the estimation, there is a method that we're using here at Chalmers to deal with this uncertainty, and that is using quantile regression. So we can apply what is known as quantile regression, and we can get the curves that tell, for example, how the curve that, so this is the 1% quantile, and this shows that we expect that 1% of the points are below this line, and 99%, the opposite, the 99% of the points would be below the purple line. So we can continue to do this for more levels, more quantile levels. And I will refer to this as quantile regression. And that is what we are using at here in the RainOverAfrica project. So to find this function f to estimate precipitation from satellite data, we use a neural network, in this case, a convolutional neural network. And to this convolutional neural network, we fit images. So an image that consists of different channels taken by this geostationary satellite that constantly looks at Africa. And we use images taken in the infrared domain. So what this means is that it doesn't matter what time of the day it is not affected by the sun. And I'm saying this because the geostationary satellite is measuring in the visible and the infrared spectrum. So by excluding information that is in the visible domain, we are able to use the same model regardless of if it is night or day. Then, since we are using quantile regression with the neural network, we are telling the neural network to tell us the quantiles of precipitation at different levels. And we are using a supervised approach. The reference data that we use is what we consider to be the best estimates from this GPM Global Precipitation Measurement Mission, which consists of rain estimates taken from a satellite that is used as the calibration satellite in this GPM mission. So just to give you the big picture, in RainOverAfrica, what we do is we take images, an image taken by this geostationary satellite, the Meteosat, that has this instrument on board, that it observes Africa in different wavelengths and different frequencies. We feed these images. So this consists actually of just one image, one observation taken, observed in different spectral channels. We feed this to a neural network, and through this neural network, we are able to get precipitation estimates for all of Africa. So this is one aspect of RainOverAfrica, but another aspect is how quickly we can get precipitation estimates with RainOverAfrica. And I've been playing a bit around with it, and I've seen that since the geostationary data, since the metasat data is published, since it is disseminated, it takes about 1 minute to get these precipitation estimates. And I have prepared a Google Colab notebook that walks you through this process of obtaining a precipitation estimate for Africa. And it goes like this. It first downloads and prepares the latest metasat observation, and it takes about 22 seconds. Now, I actually wanted to show you live this notebook, but it's a bit of a bad timing that where we download the data from is the EUMETSAT data store. And since Monday, it is not working well. So this is really bad timing for the presentation. But at the end of the presentation, I will explain you how we can also get the data that we need to RainOverAfrica without downloading it from the internet. In any case, it takes about 22 seconds to get the data from the internet and to prepare it to feed it to the network. Then it takes about 28 seconds to feed the data through the network and to get the outputs of the network. And then depending on the statistic that we want to get from these precipitation estimates, it takes between 0 and 17 seconds. So to sum up, in about 1 minute, we are able to download and prepare these images taken by the geostationary satellite, and then get some precipitation estimates like this, which shows the expected precipitation value or some uncertainty values. Now, we can get precipitation estimates from geostationary imagery. We can also get them quick, but are they accurate? In this illustration, I'm showing how RainOverAfrica is retrieving precipitation for a specific case. The precipitation estimate we get from IMERC, and then the reference precipitation from one of these GPM satellites. I could show many statistics showing that RainOverAfrica tends to perform better, but I think it is quite illustrative that we can expect that RainOverAfrica performs reasonably well, despite it only takes a minute to process. I forgot to say that, for example, for this IMERC estimate, we need to wait between 3 and 4 months. So compare this with 1 minute. That is a lot, especially if you need to take quick decisions to prepare for any possible flooding, for example. So accuracy, I think RainOverAfrica is performing quite well with respect to IMERC, but also the temporal resolution of RainOverAfrica, which is not to be confused with how long it takes to obtain the data, is half of that of IMERC. And when it comes to the spatial resolution, it is about the same with respect to the best case IMERC spatial resolution. So there's a small thing here Here I'm talking about effective spatial resolution, which is something different than the grid box resolution in which this data is provided. In this animation, I only wanted to show how precipitation evolves in RainOverAfrica and IMERC, and for example, how the satellite is observing specific, this for a small region in Africa. We don't have much time to spend in this animation, but what we can see here is that RainOverAfrica evolves more quickly than IMERC. Let's see now. And so I've mentioned a few aspects of RainOverAfrica, but a very important one is also the uncertainties that we can get from this retrieval method. So I will not spend much time in this because it's also difficult to digest. But I just want to highlight that we can get uncertainty estimates of precipitation at different levels of uncertainty. And also these uncertainties that we get are not necessarily Gaussian. Because of that, we can identify the likelihood of extreme events. So for example, let's say that we want to know how likely it is to rain, or how likely it is that it is raining above a certain threshold. So with RainOverAfrica, we can do that. So ROA is explained in a paper that is published online. The preprint is online, I mean. And we also looked into other statistics, which I present two of them here. What you see here is the evolution of rain for the months of June, July, and August for a relatively dry area in Africa. And this not smooth line, this is what we consider the best estimates from GPM. And the reason why it is not smooth is because of how much data it captures. Now, if we plot on top the IMERG evolution of rain, we can see it kind of captures the pattern, but it completely misses this peak here. If we overlay now the RainOverAfrica estimates, we can see that while the magnitude is not it doesn't agree with the GPMS estimate, we can see that the mode of the evolution of rain matches the peak in the reference. Also, when looking at year average of precipitation on the map, here on the right, we see the difference of RainOverAfrica with respect to this reference, and below the corresponding difference when using IMERC data. And very quickly, what we can see here is that there's less blue and red in the map for RainOverAfrica, which means that it approximates better the reference from the global precipitation measurement mission than the IMERC estimates. And again, to get this data, we can get this with a latency of about 1 minute since the dissemination of the data. And for IMERC, the IMERC data used for the plot below, it is not obtained until 3 months at least. So I want to start wrapping up this presentation to discuss with the audience if you have questions. And I want to wrap up a bit by listing the advantages of RainOverAfrica. So first of all, we have a way to obtain precipitation estimates that has a very low latency compared to iMERC, and also that it compares favorably in different aspects. Then this is partly possible because it only requires a single data source, which is one of the Metasat second generation geostationary satellites. And data from this satellite is released online shortly after measurements are completed. That should be the regular case, but at the moment, and while I am giving this presentation, and I tested, I checked the portal a couple of minutes before we started this seminar. It wasn't working properly. So another way to get the data is if you have a satellite antenna and you point it to one of the Nowcast service satellites, you can also get the data you need to run RainOverAfrica without an internet access. Then we can, with the precipitation estimates, we can get specific errors for each retrieval. And these errors are not necessarily Gaussian because we use quantile regression to train the network. And RainOverAfrica is a program, or RainOverAfrica is many things, but the method that RainOverAfrica is using is public, so you can actually download it and run the software to get your precipitation estimates if you wish. And if you were interested into having a more of like operational way to get precipitation estimates, you could send me an email here at amell@chalmers.ac, and I could guide you on how to get how to set up a pipeline to get near real-time precipitation estimates using RainOverAfrica. So with this, I conclude my presentation. I'm very keen now on taking questions from the audience, if you have any.
Thank you very much, Amell, Adrià, for the insightful presentation. So the floor is open now, and if you have any question, you can ask. I'm trying to look in the chat. I'm seeing there's a question. So someone says, let me get it. Great presentation, Adrià. I may have missed it, but which neural network are you using? Is it ANN, CNN? And also, with regards to the spatial resolution, are there thoughts of downloading it to more finer resolutions along the line of CHEPS and the like 5 kilometers? How does it perform with extreme rainfall events?
Yeah, so okay, these are 3 questions if I got them right. So the neural network is a convolutional neural network. It is a network that we have more or less reused. So here we are talking about RainOverAfrica, but because we are using the Metasat satellite, that is the satellite placed at 0 degrees that covers Africa. But we have also done a similar project with one of the American satellites that is not covering Africa. In that project, we had the network, a convolutional neural network. Basically, we were doing the same, estimating precipitation from geostationary satellites. And we reused this convolutional neural network that was developed in this previous work. So this should be the answer to the first question. Then with regards to the spatial resolution, so this, I understand it's not clear, but hopefully this can help you if I understood the question right. RainOverAfrica, the grid resolution of RainOverAfrica is about 3 kilometers. But I am saying that the spatial effective resolution is 50 kilometers. So this spatial effective resolution is how consistent in the spatial scales are with some reference. In this case, the reference is this data. So that is why I say 50 kilometers. That is more or less as a spatial effective resolution, but the resolution of the grid cells used in RainOverAfrica are 3 kilometers here, which is the native metacell resolution. And I think I'm reading here the chat. How does it perform with extreme rainfall events? That's something that we have not evaluated because we don't have the data for that. So if you we're keen on knowing how well it performs with extreme rainfall events, and you have some data, I will be very happy to get in touch with you and see how well it performs. But we have some contacts that have done some field work in Africa, and they have seen that RainOverAfrica performs better when detecting heavy precipitation events than other near real-time products that are operational. So I don't have any value to show how well it performs, just this input effort from some collaboration. Yes.
Okay, thank you. There's Fernand who wants to ask a question. Please, you can go ahead.
Yes, thank you, Amell, for your presentation. I really enjoy it. I was asking about the input of your CNN. What, as predictor, what are you using as predictor? And then you said that you are mapping your predictor with a ground truth value, which is also an satellite data. I was worrying about what is the ground truth of your CNN and what is the input as predictor?
Yeah, so the input to the neural network. Here, okay, let's take one step to the side and let's talk about what is the satellite observing. So the satellite is taking an image of the Earth, in this case of Africa, and it takes this image in several channels. So I'm not sure about your background, but I'm making this very simple, okay? Or I try to make this very simple. When we take a picture with our phone cameras or like a normal camera, we take an image in red, green, and blue. But this satellite is taking an image in many spectral channels. This means it takes an image in some infrared wavelengths and another infrared wavelength and so on. So the input to the neural network is this infrared image taken in different channels from this satellite. That is the input. Then the reference, as I said, it is also some satellite measurement. This is some data that has, it's already available. So we are not producing this. We just downloaded it from the internet. And that is what we consider an absolute ground truth.
Okay, thank you.
I think there's another question. Someone says, that's from Renel. He says, thank you for the nice presentation. I have what may come through as a naive question, but is image the best available method for predicting rainfall over Africa?
I'm not sure what to answer here, but IMERC is at least an established product. So that is one thing. And then when it comes to prediction, I don't think that is what IMERC is able to do, but that is not also what RainOverAfrica and many other products can do. So here we have to differentiate between retrievables, so which is so here we have to differentiate between forecasting and then retrieving an information from an image. So iMERC, RainOverAfrica, other products, they can tell with more near real time or less near real time how much it is raining right now. But this being said, iMERC, from my experience, it is probably not the best data set, but it is at least an established data set that you can use for benchmarking, for example.
Okay. There's also another question from Kellan. It says, fantastic presentation, Andrea. My question revolves around the ability of the model to encapsulate the change in precipitation patterns through the through time when making predictions, rather than just using single snapshots from the 7 channels at a certain point in time. Is the model only using rather than just using a single snapshot from the 7 channels at a certain point in time? Is the model only using a snapshot at a point in time to make a prediction at the specific moment, or does the model also ingest images from a period before present moment to make predictions at present moment?
Yeah. Yeah, I got it. It's because it's a question that formulated in different ways, but it's essentially if I am using the time dimension in the network. So the answer is no. There is different reasons why I'm doing that. The first one is a very practical one. It's simpler to not use the time dimension. But I am not using it. But it would be very simple to incorporate the time dimension into the network, because we have images every 50 minutes or something like that from the Meteosat satellite. But it can happen, for example, and this is real in my experience, that you are missing the last time step for whatever reason. So you need to start to do some smart things to compensate for missing data. But using the time dimension is something that I haven't done, but it's very should be very easy to do.
Okay. There's another question from Shukuria. He says, great presentation. While talking about the CNN inputs, you mentioned no solar contribution. Are the inputs more like radar images?
No. So, well, it depends on what you mean with radar images, but the geostationary satellites, and in this case, it has this severe instrument. So the E, I'm not sure what it stands for now, but this means spinning. This is the instrument on board the geostationary satellite that we are using in RainOverAfrica. So this means spinning something, I don't remember, visible an infrared imager. So this instrument is taking images both in the visible and infrared spectrum. So when I say no solar contribution, is that I'm excluding all the spectral frequencies for which we can have solar contribution. So we have wavelengths that are from 6.2 micrometers up to, if I remember correctly, about 30 micrometers or something like that. And radar images are the frequency of radar is much more far away from these wavelengths. I hope this answers your question. If not, feel free to ask for clarification.
I hope it does. Caleb also says, what are your views on transformer models such as Informer by Zhu et al. 2021, long sequence time series forecasting?
Oh, this is a very broad question. I'm not sure familiar now with the reference that you wrote in the chat. Yeah, I'm not sure what to answer here.
Okay.
I'm familiar with transformers and vision transformers. Here, what we just used is an existing convolutional neural network to address the problem of estimating precipitation from space.
Okay. If you also have a question and you don't want to type, you can raise your hand and ask directly. Yes, I have a question, by the way.
Yep.
If you go back to the slide where you were showing the uncertainty curves, what do you call it? The quantile regression curve.
You mean the example?
Yes,
like
no,
this one?
Yes.
Yeah.
So I was wondering, it seems that there are certain data points, certain values for which there is the intersection. And even for several uncertainty quantifications, those points will still just give you the mean. For instance, between 2 and 4.
Yeah, this point here, for example.
There's no, way of, at the moment, what you are showing, there's no way of also quantifying the uncertainty given that value range. So do you also like shift the, the magnitude of the uncertainty curves to ensure those parts are also covered or something?
I'm not sure I got your question, or maybe I confuse you. But what we see here in this point that you pointed to is that we have no uncertainty, or we have basically we are 100% sure based on the training data that the situation here, the retrieve value, the estimated value will be this value, which is about 5. So we are not doing anything special to address this, because this is directly captured by the quantiles. I'm not sure if this answers your question, or feel free to clarify.
Yes. So I thought you are defining some range, and then the uncertainty only covers values around, within the interval. But yeah, of course, what you just said means that if the value is captured well, then there's no uncertainty estimations around, right? So that.
Yeah.
Okay.
Exactly.
Okay. And also, since you are comparing with Amell, and Amell is a product that has like also historical, apart from doing. So do you have a vision of kind of also producing a product from these estimates, because you can do it from near real time? Can you do for the past images of the source data that you are using, so you can then accumulate over time so people can access those as a product also?
Yeah. So for a while, we produced RainOverAfrica estimates, and we created some data records, but we posted for practical reasons. But we can produce precipitation estimates using RainOverAfrica for past dates. So let's say you want to have an estimate for 2015, for example, we can do that. Or you can do it yourself if you, because it's just about using the code that you can get with RainOverAfrica, which, by the way, I forgot to say, you can type in RainOverAfrica.AI. That's a website, and there you will find information about RainOverAfrica. So that's one thing. Then I know there are at least 2 portals, internet portals, that are displaying RainOverAfrica. So depending on what, if you want to do a comparison, you could also use data from those portals. But if you are also interested in using RainOverAfrica estimates for some science analysis or for some comparison, again, feel free to send me an email. I'm sure we can find a way to so that you can use RainOverAfrica data, or that I can help you in setting up some kind of system that you can use to get precipitation estimates, whether that is for near real time or for historical estimates. So feel free to send me an email if you want to.
Okay. I don't see a question again and a hand up. So I think we can bring the session to a close. Thank you very much. And
yes, one more question for Amell, please. Do you think we can use such process for extreme event, like another event, like maybe heat wave or so something?
Can you repeat the question? I didn't get it.
I'm asking if we can use such a process to predict and to predict another event like heat wave, extreme event.
When you mean such a process, you mean like quantile regression, or specifically talking about precipitation?
No, quantile regression.
Yeah, so you can use that. That's why I presented quantile regression in this quite general example. So if you have data that specifically doesn't follow non-Gaussian statistics, this suits very well, but in general, and this is applicable to situations where you have uncertainty. Let's go back to this situation. Situations where you have uncertainty in the data, but also it suits very well when you have uncertainty, and this uncertainty is, let's say, not constant, like it is shown here in this plot. So if you have some other data that is not precipitation, and you want to apply quantile regression, you can think about it.
Thank you.
Okay. This was very insightful, to be honest. And we thank you very much for making the time and effort to present your work to the community. And I hope the participants learned a lot from what you've presented. And also, I hope you share the slides with the group. And yes, if you have any question, you have the email now, so you can reach out to him directly. And he's already shared some resources with us. We would send that together with the recording, and so you can look at it yourself together with the paper that he talked about. And with that, I would say thank you very much, and we'll see you again next month, everyone. Thank you.
Thank you for joining the call and for your time.
Bye.
Bye-bye.